It was pointed out to me at the end of class yesterday that I shouldn't try and add in my head. I asked how far up and how far down we go, right? I added wrong. You got to add the decimals too. Sorry. There's the correction. I'll rescan this page so it'll go up on today's notes as well. But wanted y'all to know, yeah, -1 to me. There you go. Okay. Today is question and answer day. 3, 5, 6, and 7, right? So what questions do you have? 3, 5, 3, 6, 3, 7. Yes, ma'am.
31 in the context of 44. It's like take the third derivative and evaluate that. X equals 4.
So let's take a look at 3, 5, number 35. So we have this disgusting ugly mother here, 31. This one. Okay. So not just the first, but the second and the third. Okay. Let me copy down that equation. X squared minus xy minus y squared equals 1 at the point 2, 1. Now, the difference between this and 44, just to start, 44 didn't give me a y value, right? It just gives me an x value. So I have to figure out the y value that goes with that to start. So once I've done that, I'd be in the same boat I am here. But that just means take your x, plug it in, solve for the y. All right. So I want implicitly the first derivative. So I take the derivative with respect to x everywhere. Derivative of x squared is 2x. I have a product, x times y. Derivative of the x times the y, plus leave the x alone, take the derivative of the y. Then I have the derivative of y squared, which is 2y. Chain rule gives me the butt weight there's more. Uh-oh. Derivative of 1 is 0. Got to take the derivative everywhere, both sides. My goal is to get y prime alone. So distribute the minus sign and then we'll rearrange. From here until I get y prime equals, it's nothing but algebra. These two pieces will go to the other side. Which I will factor the y prime out of. And now I have y prime. Now you said at this point, right? At the point 2, 1. I have x is 2, y is 1. Just plug those in. Y prime at 2, 1 is 3/4. Perfect. Wonderful, marvelous, beautiful. Now comes the sucky part. I want the second derivative. Y double prime means I got to take the derivative of this. Quotient rule. Derivative of the top. Well, derivative of 2x is 2. What's the derivative of y? Times the bottom. Minus derivative of the bottom. times the top. Over the bottom squared. If all I want is the second derivative, I could just plug in right here. I could plug in my value for x, I could plug in my value for y, and I can plug in my value for y prime. But that's not where this problem ends, right? I want to get to the third derivative, so I probably want to simplify this, see what cancels to make my life easier, because I'm going to have to do another derivative, and that means another quotient rule. The top is already disgusting. Let me see if I can make it nicer. 2x minus xy prime plus, no, this could become a minus. Minus, wait a minute, I'm losing track. 2x minus xy prime plus 4y minus 2y prime minus the whole thing, 2x plus 4xy prime two x 4xy prime minus y minus 2y prime. All over, I got to do the bottom squared, x squared plus 4xy plus 4y squared. So far, so good? All right, what's going to cancel? I got a 2x here, I got a minus 2x here. I have xy prime, I have more xy primes. I have y's with y's, and I have y, minus 2yy prime, minus 2yy prime. Those are going to cancel. Everything else is just going to gather. So minus an xy minus 4, more of them is minus 5, xy prime. 4y minus minus y becomes plus 5y. There's my second derivative. We need the value at our point before we do the third derivative. So I plug in x is 2, y is 1, and y prime is 3/4, because we got that right here. And I get y double prime negative 5 times 2 times 3/4 plus 5 times 1 over 2 squared, 4 times 2 times 1, 4 times 1 squared. So let's see, 10 times 3/4 is minus 7.5. Plus 5 over 4 plus 8 plus 4. I get negative 2.5 over 16 or minus 5 over 32. If you'd rather give me a decimal, that's perfectly fine. I'm not going to throw a hissy fit. Questions so far? I need a third derivative. Quotient rule again. Now, I believe in our problem, this is going to get fairly long. So you might not be able to write it all across on one line. That's okay. I need the derivative top times the bottom, derivative bottom times the top. I could put all of those as separate and then just plug in the numbers. I think I have enough room to do this one. So my third derivative, taking the derivative of this. What's the derivative of 5x? Just 5. Leave the y prime alone. Then leave the 5x, take the derivative of y prime, that's y double prime. Derivative of the top times the bottom. Minus derivative of the bottom. Derivative of x squared is 2x. The derivative of 4xy is 4 times 1 times y plus 4 times x times y prime. Derivative of 4y squared is 8y y prime. Derivative of the bottom times the top. Oh, that means I forgot something. Up here. When I did the derivative of the top, what did I forget? I did the product rule here. I forgot to do the 5y. There should be another 5y prime there from this derivative. I got to do all the derivatives. I can't just forget one. This is all over the bottom squared. Are you all ready to run screaming for the hills yet? Okay. I'm not going to simplify a damn thing here if I don't have to. Because all I need to do is plug in the numbers. You want y triple prime at this spot. You have a value for y double prime. You have a value for y prime. You have a value for y. You have a value for x. You can just plug numbers in and walk away. Best part, you've already plugged some of these numbers in. X squared plus 4xy plus 4y squared. You did that right here. I know this entire bottom is 16. I don't have to do any more work on that. I also notice right here, those two are going to cancel. But now it's just plug in all the numbers you've got and give me a number. Is it short? No. It's taken me 13 minutes to do this one problem. I don't care, but I'm telling you right now, it's slow, deliberate, and careful. You saw what happened when I wasn't careful. I dropped something. Oops, I got to go back and fix that. So we must be very diligent in doing this set of derivatives. Does that make what we need to do in 44 clearer? Okay. I will freely admit, I thought it was a second derivative, not a third, which meant I would have stopped right there and not had to do this extra quotient rule. But that's okay. Yeah, I got to plug numbers in now. I'm sorry? How? Chloe, I can't hear over this, please. So here, you left it like that? Absolutely, you can plug in there. You can even take the derivative from there, do the second derivative, but remember the implicit derivatives. You don't have to do the simplifying until after you've plugged in numbers. That's perfectly fine. Because once I have an implicit equation, I can take the derivative of it. Is the simplifying gonna help? Maybe, maybe not. Depends on how much you like algebra. But it absolutely works that way. Okay, let's try it the other way. Absolutely. So if I start from here and I take the derivative again, derivative of 2x is just 2. The derivative of y is y prime. Here I have a product rule, and here I have a product rule. And there'll be some y double primes floating around. Separate those after you plug in the numbers. But that's repeated product rule instead of repeated quotient rule. Product rule is easier. Let's use that. I like that. It's a good move. More questions. 3.7's 10b. So the problem we did was number 9, right? And we asked for the velocity. Right. So let me just adapt that problem. So we had the height equation for that problem was 2 minus, no, plus 24.5 t minus 4.9 t squared. I just put that piece of paper away. Our maximum height in that problem was 32 meters, right? So what if I asked, what's the speed on the way up at 20 meters? Okay. Find velocity at a height of 20 on the way up. Well, if I know the height is 20, I can put that here. Now you can tell me when we're at 20 meters. Sorry, yeah, in this case, meters. In problem 10, we're in feet. Units are irrelevant. You can tell me when we're at 20. All you have to do is solve the quadratic equation. I move everything from the right to the left. So I subtract, copy error. Copy error. Can't lose the t. Okay, out comes the quadratic formula. There's my quadratic formula. Right. We hit the ground at 5 point something seconds. That makes sense. So we're going to be at 20 meters at 2 points in time, right? Once on the way up and once on the way down. Which one's on the way up? The first one. I should go up before I come down, right? So this is my time going up, the 0.89 seconds. That's the number I'm going to use to find the velocity. I know that the time as many decimals as you want. The velocity at that time, we have our velocity equation. So I plug that in. My velocity is 15.7 meters per second. I hope so. That's a program in my calculator. So I don't know, do you have a quadratic program in your calculator? I have lots of programs in my calculator. If you don't have the quadratic formula already programmed into your calculator, then you need to write out the quadratic formula. X is equal to negative b plus or minus the square root of b squared minus 4c all over 2a. I can't say it anymore without singing the stupid song. It's stuck. As a matter of fact, if we put in the 4.1 seconds, we should get a negative value. And that'll tell me I'm coming down instead of going up. This velocity being positive means I know I'm going up. Because that time I was asking, when did we hit the ground? Can I go back in time? Not unless I'm doing 88 miles an hour in a DeLorean, right? More questions. No, but I'll do something similar to it. Which one's 26? 26 is my chemistry reaction, right? Take a look at 23. Same section, all letters, no values. Problem number 23 says the force acting on a body with a known mass m and velocity v is the change in momentum. Force is mass times acceleration, right? That's Newton's second law. But acceleration is the derivative of velocity. So I can think of this as the derivative of mass times velocity. That's, as far as Newton knew, that's perfect. That's wonderful. Einstein showed that the faster you go, the harder it is to accelerate. It takes more energy to accelerate as you go faster. And so your velocity kind of changes. And the other way to interpret that is to say that your mass changes. It's harder to accelerate because you weigh more. If something's harder to accelerate, it's resisting the acceleration. That's what mass is. It's resistance to acceleration. Force is mass times acceleration. So I want to think of changing mass. The mass is actually your resting mass, the mass when you're not accelerating, times 1 minus v squared over c squared, where c is the speed of light. This is Einstein's equation on the relationship between mass and energy applied to mass. As I push more and more energy into the system trying to get to accelerate, some of that energy is converted to mass rather than acceleration. You get heavier. Einstein's weird, man. Okay. I want to know how force changes. So I want to use this calculation. I want the derivative of mv, but I want to use this for mass. Okay, Mariah, do you want to do quotient rule or product rule? Okay, product. That means I'm going to take that square root thing out of the bottom, which means I'm going to have stuff to the what power? There's a root. So this is the derivative of m naught v times 1 minus v squared over c squared to the negative 1/2. M naught is a constant. C is a constant. The only parts that is not a constant is V. That's the thing I want to change. So this is a constant. It's going to stay there. The derivative of V, no idea. dv dt. Leave this part alone. Derivative of the first times the second. Plus, leave the first alone. Now we're going to get rid of the second. Chain rule, because it's ugly to the minus 1/2. Right? So I get minus 1/2 ugly to the minus 3/2. Stuff inside does not change. But wait, there's more. Now I need derivative stuff. What's derivative 1? V squared. C squared's a constant. I can leave it there. What's the derivative of V squared? But wait, there's more. When I took the derivative of V, I got a dv dt. So I get a 2v, but I also should have stuck right in there dv dt. All right, hang on a second. This m0 dv dt over ugly in a square root. Right? That's what the negative 1/2 power means. This is to a negative 3/2 power. Bleh. So far, so good? I just put it in the bottom. Haven't dealt with the top at all. What's left behind? Another m0 and a v. But there's a negative 1/2 here. Let me put the negative there. Wait, there's a 1/2 here. There's a 2 here. Those will cancel. So I'll get v over c squared and a dv dt. Two v over c squared, that's going to stay on the top. But the 2 cancels with the 1/2. The minus went here. This stayed on top. This stayed on top. This stayed on top. I'm sorry? Here. The first part of my product rule. Part 1, part 2. So far, so good? It's gross and disgusting, but it seems to be right. Now, they actually give me a formula in the book that this is supposed to end up looking like. Ready? Here's the page from the textbook. Show that when you do this derivative, you get this thing. m0a over 1 minus v squared over c squared to the 3/2. I have exactly that right here. I just have a bunch of other junk, and I have this fraction that does not have a common denominator. I need a common denominator. So M0 dv dt times something. I need this to end up being 1 minus v squared over c squared to the 3 halves. Right now it's to the 1/2. That means I need another whole 1, right? That means I'm going to need one of them up here. To the first power, to the 3 halves power. Minus, now let's look at this part. Hey, wait a minute. I've got an M0. I've got a dv dt. And then I've got v squared over c squared. This v, it got combined with this one to make the v squared. That's all on the same denominator, right? It's all on the same denominator that I can combine the tops. Notice there is an M0 dv dt in both of these. I'm going to factor that out. What's left behind from the top of the first fraction if I factor out the M0 and the dv dt? Oh, just this part. 1 minus. Oh, see, I made a sign error and we just have to find it. Hang on a second. I need to back up. I made a boo-boo. Here. Tell me where my boo-boo is. It's in this set of parentheses right here. What's my mistake? Let's walk through that derivative again, right? This is the derivative of the bottom. This part. So I have the negative 1/2, ugly stuff to the negative 3 halves. And then I take the derivative of the inside. What's the derivative of v squared? But it's being subtracted. I forgot to bring over the minus sign. There should be a minus sign right here. And if that's a minus sign, what happens here? That becomes a plus. And that becomes a plus. And that means right here, it's plus v squared over c squared. What happens to those two? And that's the formula I wanted to get out of the book. You see how I needed to do the algebra to convert the formula I got into the formula they wanted. In our chemistry problem, number 26, that's the same thing. Take the derivative you calculate, do a bunch of algebra, and make it look like the formula they wrote down. Now they actually have like an X in there, right? In problem 26, they have an X. Right. But then later they say, make this X. Well, our formula never had an A in it until the very end, because A is the derivative of velocity. So I have to remember that substitution to make it look like what they wanted in the book. I have to remember that I'm working in X have to make the change to make things look like X. I will freely admit that now I have this formula. Now I can use it from here on out, and that's going to make me pretty happy when I'm doing physics involving relativistic behavior, which of course happens so often, right? But the distinct advantage to this problem is that having done it formulaically once, I don't ever have to do it again. I have this formula in front of me now for use wherever I want to keep working with it. If I'm going to do a lot of chemical concentration problems, do I want to do a derivative over and over and over and over again? No, let me just do it once with all the formula, all the variables in there, and then I can just plug in the numbers for each different chemical. More questions? All right, it's the algebra. It's always the algebra. It's not the calculus. The algebra sucks. Yes, ma'am.
16.
Six.
Well, like 16.
16. So 16 is dropping a stone and looking at a ripple.
Yeah.
Look at 17. 17 is a balloon. I have a balloon. I drew a horrible sphere, but there we go. Find the rate of increase in the surface area. And they give me the formula for surface area. With respect to the radius, when the radius is 1, 2, and 3 feet, right? So I want ds dr. The difference between this and problem 16 is that in problem 16, they told me how fast the radius was changing, right? So I'm going to make up a number. Now this looks much more like problem 16, doesn't it? All right. If the radius is increasing 1 inch per second, then I can write an equation for the radius in terms of time. The rate of increase is a constant. It's 1. What graph has a constant slope? A slope that's always the same. A straight line, right? And in this case, I'm telling you the slope is 1. So that means that r should be 1t. Well, I can change my formula. And I can write surface area in terms of time, can't I? Now, in this case, I picked 1. I think in 16, the number is 60, not 1. So I'm going to make believe it's not just a 1. I want to take the derivative of this to get ds dt. That's a chain rule problem. 4 pi are numbers, ugly squared. I know how to take the derivative of that. What's the derivative of ugly squared? But wait, there's more. What's the derivative of t? Just 1. Now, if it was 20t, then the derivative would be 20. If it was 7t, the derivative would be 7. If it's 60t,
That's a circle. Five, one squared.
that's the formula for the area of a circle. That's all I need. But the process is still the same. If I asked about the volume of the sphere changing instead of the area of the sphere, then I could use the formula for the volume instead. And I'd have 4/3 pi r cubed. That's fine. Why would I want to know how fast the radius is changing when I know the volume is changing? Why would I want to know how fast the radius is changing when I know how fast the volume is changing? Where can a balloon save your life? They do. When you have a nosebleed, they inflate a balloon, put it up in your nose, stop the blood falling. I have seen my favorite use for something to put up my nose when I have a nosebleed is a tampon. It's really, really absorbent, designed to absorb blood, stick it up your nose, works perfectly. It's the best thing. But I don't get nosebleeds very much anymore. My son used to get them regularly. So we always carried tampons everywhere we went. However, where can a balloon save your life? Nosebleeds are rarely life-threatening. Rarely. They can be. Car accident. Your airbag's a balloon. I want to know how fast the radius of that balloon is going, because I want to know how fast it's going to hit me in the face. If it's going too fast, it may save my life, but break my nose. I wear glasses. It may break my glasses directly in front of my eyes. I need to know that. I need the safety strength of the glasses, and I need to know if my impact with that balloon is going to damage my eyes. That's actually checked by the National Highway Traffic Safety Administration when they do car crash tests. They have crash test dummies that wear glasses to check that. Useless problem. I'm never going to use it anywhere. And now I have a rate that changes for surface area. Hold that thought. We're not there yet. There's a whole section on this. Related rates. I know exactly where you're going with this. That's Wednesday. Sorry, Thursday. There's another way to do this problem. We'll do it on Thursday. Yep, give me a number. You could. You don't have to. You're just plugging in numbers. You can plug in the unsimplified version. For the rate. Aha. Oh, why not? My ripple is expanding. Right, but that converts time in seconds to a distance. Because the radius of a circle has to be a distance, right? I need to move from time to distance. You were asked how fast is the circle moving at a given time? Canceling out my units. Hold that thought. We'll make it make sense later. I promise.
I can't come see it.
That's good. You've learned something. It should be uncomfortable. More questions. Yes, ma'am. Silly questions. I like silly questions.
One side is negative 1 times a bunch of them plus the 1 times 1 and 0 1.
Only if the junk is the same. You'd have minus thing plus other thing, they don't cancel. Minus thing plus the same thing, they would cancel. The things would cancel. Otherwise, you can, if it's a 1, you can just get rid of it because 1 times stuff is stuff. If it's minus 1, then you need to leave the minus sign with all the stuff. Even if it's on the outside of the parentheses. Yes, Nicole. I wouldn't.
Words are.
4 pi 2 times 3 times 1 times 1. So you just put in the bigger number. Yes. Okay. The number could be in the hundreds of thousands. You think about this for a second. You've got a circle that's, I don't know, 60 centimeters in radius. 60 centimeters is 2 feet. So that's a circle that's 4 feet across. What's its area, and how fast is that area getting bigger? A lot, isn't it? You've got to turn these numbers into numbers that make sense to you intuitively. 60 centimeters, 22,500 square centimeters. The number sounds weird. Yeah, turn it into square inches or square feet. And then you might have a more intuitive understanding of it. Knowing and internalizing those units makes a difference. 2 things. This is due next class, Wednesday. Fall break is Monday and Tuesday. Second, Thursday. Thursday, we're going to do another thing like we did the other week. I'm going to have to pre-record the class. I will remind you of this on Wednesday. We will not actually physically have class in this room on Thursday. There will be a recorded version on YouTube for you to watch. I will do it at home over the weekend, but it'll be available to you. I'll remind you on Wednesday. I will see you on Wednesday. Enjoy your break.